Today I'm going to be talking about the work we've been doing in applying reinforcement learning to accelerate real-time risk calculations. The first thing I'll do is I'll introduce the specific sort of risk problem domain that we're talking about. Then we'll take a brief look at some sort of introductory reinforcement learning stuff, and then we'll move on to see what happens when we apply one to the other. So the domain we're looking at is very much sort of interest rates. So what we are needing to do is to build a lot of different zero curves and many curves across many currencies. So in dollars, we'll have a SOFR curve and a 3-month LIBOR curve and a 1-month LIBOR curve and a Fed fund curve. In euros, we'll have EONIA and Euribor, etc. The interesting thing is that there are dependencies between these curves. So in order to build the 3-month dollar LIBOR curve, we need to already know the SOFR zero curve. And because the 1-month LIBOR curve is quoted using basis swaps between 1 month and 3 months, we need to know both the 3-month LIBOR curve and the SOFR curve before we can compute the 1-month LIBOR curve. Now, we're considering many sorts of analyses that we need to perform, including mark-to-market P&L, hedging, stress testing, historical VAR, margining, CVA. All of these are fundamentally driven by evaluating a lot of trades, portfolio trades, against a whole series of curves which are derived or perturbed in some way. So we're going to need to build a lot of curves, and we're going to need to do it quickly in order to produce sort of real-time or quasi-real-time results. So we manage the relationships between sort of the market observables and curves and other curves using a dependency graph. And what we'll do, take a very simple example here just to illustrate what we're talking about. So imagine that we have a very simple world. There's only 3 curves. We're doing a simple bucketed PV01 analysis and producing some sensitivities. There are only 2 tickers in each curve. So this is what our sort of base market scenario looks like. We have a SOFR curve, a 3-month LIBOR curve, and a 1-month LIBOR curve. I've named them here with a suffix, which is MKT, just to say that this is the market scenario. The SOFR curve doesn't require any other curves in order to be built. It just requires the values of its 2 tickers. The 3-month LIBOR curve requires its 2 tickers, but it also requires the SOFR curve to exist. And the 1-month LIBOR curve requires its tickers and the 2 other curves already to have been built. If we look at one of the scenarios, so one of the scenarios which might be the case where the 1-year SOFR rate has been perturbed by 1 basis point, then again we have 3 different curves. And I've named them all with the suffix that corresponds to just the name of the scenario. And it's basically the same idea as before, except that obviously we're perturbing one of the tickers by a basis point. And when we say that the SOFR curve here needs to exist, it's the specific one that belongs to this scenario. So we can sort of visualize things in a table where we have the names of each of our scenarios along here and the different types of curves that we require in the columns. And what we see, for example, is that if we look at a 1-month LIBOR scenario, then the SOFR curve that we use there is the base SOFR curve. The 3-month LIBOR curve is also the base 3-month LIBOR curve. And it's only the 1-month LIBOR curve that needs to be rebuilt. Everything else can be reused. Similarly, for the 3-month LIBOR scenarios, we need to build the 3-month LIBOR and the 1-month specific to that scenario. The SOFR curve can be used just using the market curve. So the dependency graph tells us which curves that we need to rebuild whenever something that we can observe in the market changes. And it tells us in which order we need to rebuild them. Okay. Now, in fact, I guess what it really tells us is a valid order. There are obviously many valid orders, and we don't really care for our purposes which valid order, because the tree can be traversed in many ways. All that we care about is that the end result is valid. So if the 1-year SOFR point changes, we have this big list of curves in our little world that we need to rebuild. If the 1-month LIBOR 10-year point changes, we only need to rebuild a far smaller list. So this is telling us how to avoid any unnecessary computations. But in the real world, there are many more curves than we have in our example. Each one of those will have many more maturities. Maybe it'll have 30 or 40 points on the curve. And there are many more scenarios that we're interested in order to be able to conduct all of our different analyses. And we want all of those results pretty quickly. So we also are going to need to distribute these computations in order to be able to get the results in the time frame that we require. So the question is how to distribute this minimum set of computations. Now, it seems like that should be trivial. But in reality, not all market variables change at the same time. So at any one moment, we might have to rebuild a different subset of the nodes on the tree. There are dependencies between the tasks. So for example, we can't assign say, task X to compute node 1 and task Y to compute node 2 if task X requires the result of task Y in order to be computed. Okay, so there are dependencies that we need to worry about. On top of that, different compute nodes will be running at different speeds, and those speeds will be varying over time. And there are costs to serializing, communicating, deserializing in order to do this distribution. Some of those costs are fixed on a per call basis. There are linear with the number of computations that go into a call. And therefore, it may often be efficient to batch some computations together. Different tasks will also involve different amounts of work. So if you look, you might have a curve which is only 10 years long, and the instruments that go into building that curve have a nice, simple annual cash flow based on a simple interest rate. Or the curve might be 30 years long and might require you to use instruments that have the arithmetic average of the overnight rate. Obviously, the computational burden of the two is quite different, and we kind of need to know that when we look for a good strategy for distributing these calculations. So the ideal solution to what seems to be trivial, I feel, ends up being relatively complex and dynamic in nature. So if we sort of look at this, we have an agent that's kind of sat there interacting with an environment. It receives a list of tasks that it needs to distribute. And then the agent uses its policy to distribute those tasks, or to schedule those tasks, and then observes the amount of time that the environment takes to execute that. And then based on that, it adjusts its policy, optimizes things, and repeats, and hopefully is more effective the next time around. Now, in reinforcement learning, typically, we have an agent, and the agent observes a state. It takes an action, submits that action to the environment, and the environment returns some sort of numeric reward and an update on which state we're now in. And then obviously the agent learns and proceeds. So it kind of feels like we have a reinforcement learning problem on our hands. Now, the starting point in reinforcement learning is always to sort of figure out what does the state look like and what do the actions look like. In our case, the actions are going to be things like this. So schedule task 1 onto compute node X, or maybe schedule tasks 2 and 3 to compute node Y, and schedule tasks 4 and 5 to compute node Z, or Z. And obviously the other type of action is say, dispatch all the calculations that I've currently scheduled and execute those. Now, imagine that we have even just 200 tasks that we need to schedule, and we have just 5 nodes in which we're going to distribute them. Each task could be assigned to any one or more of the nodes. And as we'll see later, some duplication is often optimal. So in the usual sort of encoding, that would mean that we have something like 1,000 binary elements in the action array, which gives us 2 to the 1,000 possible action configurations, which is whatever that is, 10 to the 300 or thereabouts. So it's a vast number of possible actions. When you consider most sort of simple reinforcement learning examples, most reinforcement learning examples that people see, it's playing a video game, and the actions are either like left, right, or fire. So we're talking bigger numbers here. So it makes sense to break the action into sort of smaller steps. So what we do is we say, we'll just schedule one task to one node in one action, and the other action will be dispatch all the scheduled tasks for execution. In this case, we effectively now have a vector for the action where the number of items in the action is sort of the sum of the number of tasks and the number of jobs rather than the product of the two, which is obviously a lot smaller. The state, if we look at the state, will be comprised of three things. One is an encoded list of all of the tasks that need to be computed. The next is a list of the tasks that the agent has already scheduled using its actions and which nodes they're being scheduled on. And obviously the agent needs to know this in order to kind of understand what it's in the middle of doing. And also the current speed, if you like, of each of the compute nodes. The agent will receive ultimately a reward, which will be the negative of the elapsed time at every step, since obviously our objective is to get the results faster rather than slower. And we'll also give the agent a small positive fixed bonus for completing the work list. This will be done sort of in an episodic fashion. So the episode will start with a list of the work that needs to be performed. The agent will loop through scheduling and dispatching the work until it's complete, and then another episode will begin based on whatever changes have occurred in the market since the last one. So to start with a few definitions here, we define G to be the return that is realized in terms of the rewards during the episode. So here, this is, RK is the return at time step K. Gamma just discounts everything back to the start of the episode. And the discounting is important because that obviously allows us to prefer to get the reward sooner rather than later. And it also allows us to prevent G from becoming infinite. Okay. Now, the next thing we'll see on here is requires us to define the policy. So here, pi is the policy, which is effectively expressed as the probability of taking action A given that we're in state S. So then we define V to be the value of being in a certain state, and the value of that state, given this policy, will be the expected value of G given that we're in that state. So if we look at that, then here we're basically just summing over all the different actions that are possible in the state, the probability of that action, and then here we have the outcome of that. So there's obviously a series of possible successor states, if you like, and rewards that can occur. So we take the probability of those given that we're in the world we're in and taking the action we're taking, and just multiply that by the reward plus the one-step discounted value of being in the following state. So those kind of fairly standard definitions. The learning takes place over time steps, and in the sort of standard dynamic programming approach, we would use a tabular representation for the value functions and so forth. Now, our state space in reality is just too large for a tabular solution. So we're going to use some function approximators. This means that we're going to define the state value as a function that's dependent on a set of weights, W in this case. And then our objective is now going to be to learn those weights such that we end up with a good approximator for the state value function. And our approximators will be neural networks. Now, if we look at the policy, so here, the question we have to answer is, given that we know the estimated value of being in any state, how do we choose which action to take? So the most trivial or obvious is to do an argmax across the actions. So we choose the action that takes us to the state with the highest estimated value. Now, obviously the problem with that is the classic sort of exploration versus exploitation dilemma. So if we start out knowing very little about our environment, if we always choose the action that leads us to our estimated best state, we might never learn that there's actually a better state, or an action that we could be taking that would lead us to a better state. So it can be advantageous to explore what appear to be worse options, rather than always following the best option. Conversely, if we never exploit our understanding of what the best choice is, then we won't get good behavior. And since in the end, our goal is to have an agent that performs well, we need to be able to exploit things. So one of the things that people start doing at this point is they use an epsilon greedy approach. And what this means effectively is that they will choose the best action, say 95% of the time, in the case where epsilon is 5%, and then they will select actions uniformly at random for the remainder. But there's all sorts of ambiguity around this. What is the right level of epsilon to use? We might start with a high epsilon and decrease that over time. And also what happens if after a while the environment changes? So things have been stable, we've decreased the epsilon, now the environment has changed. Logically, we need the epsilon to increase again. But how would we know that, and how would we control it? So remember as well that our agent is operating in the real world, not training first and then being deployed. So its learning is very much online. So what can we do? Well, the obvious thing to say is, let's try allowing the agent to control its policy as well as its valuations. So the type of algorithm that we're going to use is known as an ACTOR-CRITIC method. So here we have two approximators. We have one approximator for the state value called the critic, another approximator for the optimal policy that we'll call the actor. The critic updates based on sort of observed error in its estimates. So as it moves from one time step to the next, takes an action, looks to see how far off the new value is relative to what it expected before it made the move, and that gets fed into the backpropagation. The actor uses a softmax activation. So basically, it's going to compute some value h for each possible action, convert those into a probability, and then sample that. The actor will do its updates using a similar update to basically take the critic loss and then multiply that by the derivative of the log of the probability of having chosen that action, given that we were in that state. So how do we implement this? Well, this is all implemented in Python using PyTorch. The critic has a number of input nodes, or number of nodes in the input layer, which corresponds to the number of elements in our state. Then it has two fully connected hidden layers, 256 nodes in each layer, with rectified linear activations. It has a single output node with a linear activation. The actor is very similar to the critic, but in its output layer, it has more nodes, so it has one node corresponding to each possible action, and it uses the softmax activation on that. The agent runs locally on our computer, and then dispatches the schedule for execution of the tasks onto some series of compute nodes on some sort of grid. And those tasks might be executed either on AWS. When we do it in AWS, we kind of use old-fashioned things like EC2, because that way we're not encountering any of the sort of elastic features of AWS. And once you start encountering those, it becomes very hard to determine how much of the performance is driven by your algorithm and how much is driven by what AWS is doing in the background. So with EC2, we can have a fixed number of nodes, and then we can at least understand the results. And then we also have a simulator that we run these things in, and that allows us to control every element of what happens directly, which is useful because then we can see how the agent responds to a particular situation without having to wait for that situation to arise in the wild. So here's some results. So this is for the case where we have just 33 jobs and just one node. So this is kind of like an introductory case. The orange graph shows how many steps are required to build the schedule. Here we see how it evolves per episode. So at the beginning, it's taking a fairly large number of steps. By the end, it's clearly converged to what would be 34 steps, which would be basically 33 schedules followed by one execute, dispatch. If we look at the blue graph, shows us how many dispatch actions are occurring during each episode. And here we see, obviously, it flirts with the idea of doing multiple dispatches, but then ultimately stabilizes at one single dispatch per episode. Now, in this case, this makes sense because we have a nice simple environment here where all the market data is updating at the same time. We only have one node. It's a small problem. The node speed is constant. All of the tasks require the same amount of work. So there's nothing sort of surprising in this result. It's the result that we would hope to get. So the question is, what happens when we increase the size of the problem? So here we see that just increasing from having 30-something jobs to 200 and something and leaving everything else the same, all of a sudden, rather than this thing converging, that even within like 250 steps, it's already taking 50,000, even within 250 episodes, it's already taken 50,000 steps to build the schedule, which is obviously nonsense. So it's clearly fallen into a hole at that point, and it just grinds to a halt. And yet here we haven't introduced any of our complications from the real world. So still one node, constant speed, et cetera, et cetera. So what's the problem? Well, the main problem is that the rewards are very sparse. So the main reward comes at the end of the episode. The state space and the action space are both pretty large. An episode can comprise hundreds of steps. And when the agent gets to the end of the episodes and receives its bonus, it needs to somehow understand that that bonus belongs not just to that last action, but to the whole series of actions that took it there. And that is basically a classic credit assignment problem, where the credit for the reward needs to be shared in some way among all the steps we took. And if we don't do that, the agent won't learn sort of early in the episode to make good strategic moves, and then we just won't have good behavior. Now, in fact, one-step updates can eventually achieve that, but they only bring the knowledge of the reward slowly and slowly nearer to the start of the episode. And so it can take a long time to learn, or it can simply fail to converge at all. So beyond one-step updates, what can we do? Well, as a type of eligibility trace, we can move from one step to n step. And I guess the question is, what's the right value for n? So if n is infinite, we basically have Monte Carlo. So it's a different world altogether. But if n is 50, we found that worked pretty well. And it also works a whole lot faster. And I guess the reason it's working faster is simply that it's doing the back propagation part of the whole thing far less frequently. And therefore, it's able to move forward much, much quicker. Another thing we can look at is reward engineering. So if you recall, our reward function was basically to say that we take the negative of the time taken at every time step, and then we just have a small fixed bonus at the end. So what we could look at is providing more rewards earlier in the episode to help encourage the agent to learn to go in the right direction from the start. But the reality is that if we know what the perfect reward function is that encourages the correct behavior in every state, then we probably don't need reinforcement learning. So it's really because of the fact that we don't know what the correct reward function is that we need to do this. Which means that reward functions are inherently imperfect. And from my own somewhat naive trials and errors, I'd find that I had to have some clever idea for how I can tweak the reward function to encourage the right behavior. And indeed, it would work. You'd see things would start converging quite nicely. And then all of a sudden, there'd be some side effect that I hadn't anticipated, and it would fall into a hole. And it was always better in the end to keep the reward function as simple as it could and to give the agent time to do its exploring until it learned what it needed to learn. Feature engineering. So another thing we can do is we can look at the state. And we can intelligently choose features to add to the state that will help guide the agent through the learning process. Now, we could, for example, say, rather than having the agent learn the dependency graph just through trial and error, then we could encode a representation of the graph into the state, and then it just should be easier for the agent to learn that. But clearly, this increases the dimensionality of the problem. So in the usual encoding, if we have n nodes, then adding the dependencies would require, or n nodes in the dependency graph, it would require adding n squared extra elements to the state. And that just in itself makes the learning more difficult. So, the interesting thing is that the dependencies themselves, in the way we formulate this problem, the dependencies themselves are static, so they don't need to be part of the state. And it just turns out to be easier for the agent to learn relatively complex things in lower dimensions rather than relatively simpler things in higher dimensions, given enough time and a good algorithm and so forth. But as the problem size grows, then it becomes more difficult to converge again. So the question really is, can we make some changes to our environment that will help? Okay, so this feels a little bit like cheating, but the reality is that this is information that we know and that the environment has access to. And we really need our agent to be focused on learning the bit that we don't understand rather than the bit that we do understand. So in our case, what the agent can figure out is how to schedule these tasks optimally in a dynamic environment. So let's do a few things to make it easier for the agent. So the first thing that we do is we add what we call a cleanup node, where we take one of the compute nodes that we have, and we reserve that for this purposes of what we call cleanup. And then we allow the agent to say, okay, I finished scheduling everything I'm going to schedule. Now do all the remaining work on that one sort of hidden node, one hidden compute node. And the next thing that we allow is for an automatic cleanup and dispatch after X steps. So after, say, 400 steps, the agent is basically forced to say, okay, clean up everything and dispatch. This ensures that the agent completes the episode within a finite amount of time and is therefore able to learn and improve. So it doesn't get to the situation where it's in 50,000 steps per episode and things are just getting worse. The other thing that turns out to be useful is to have auto-scheduling of missing requirements when we add a task. So if the agent tries to add to a schedule for a particular compute node the 3-month LIBOR task, and the SOFA results are not available for that compute node, then the environment will just say, okay, I'm going to add the 3-month the SOFA computation to that schedule for you as well. Now, the auto-scheduling is actually very helpful because it enables the agent to construct the schedule in fewer steps. This is valuable because each step requires a forward evaluation of two neural networks, so it takes time. So if we can reduce the amount of time, then obviously that works in our favor. And the agent is rewarded in general to minimize time since that's the objective, so that all works out quite nicely. Now these changes don't automatically provide good results, they just make the rewards less sparse, which enables the agent to get working on learning things. So if we now look at what happens when we take our 204 tasks and 5 compute nodes here, with the n being 50, now we see it converges quite nicely. So if we look at the orange graph, the number of steps to build, this ends up being around 60 steps to build the schedule. And I at least find that fairly interesting because we know there are 204 jobs that need to be scheduled, and it's scheduling them all in like 60-something steps. So, given that I know from looking at the tree that there are about 100 leaf nodes, and the leaf nodes need to be manually added. We can't get those automatically for free because the starting point is basically the leaf, and then the parents get added for free. So on that basis, we would expect 100 steps. Now we know that there is this cleanup node, which we can assume is doing roughly 20% of the work. So we'd expect it would require 80 steps, yet somehow it's getting to 60. So, to me that's interesting. When I look at it more closely, it turns out that it's basically learning an optimal, which is, in a sense, a function of the shape of the tree. It realizes that certain schedule tasks that it can do automatically bring along a lot of parent nodes, if you like, and others don't. So it figures out that it will basically build as much of the schedule as it can efficiently using its scheduled tasks, and then dump all the remainder, because it gets all the remainder in one step, onto the 5th node. Obviously, the quickest it could produce the schedule would be just to implement the cleanup from the start. But if it did that, in that case, we would see a number would be 200 plus for the time, whereas here we're seeing something which is a small fraction of that. It's like 44 on the units that I have here. Here we see basically the same work. We just see how it's distributed across the different compute nodes. So at the beginning, it's a little all over the place. There's obviously more work happening on the cleanup node. By the end, everything is stabilized to a nice even fraction for each of the nodes. But the thing that's interesting to me here is that the level of this is clearly above 204. So it's clearly doing more work than we would like naively expect that it would be the optimal amount. And it seems that what's happened here is that the agents worked out that based on the dependencies within the graph, it makes sense to say, put the SOFA curve building into each one of the nodes, because that result can be reused straight away on the other ones, as opposed to breaking the whole thing into multiple steps, which would just take more time with the communications and lead to more waiting. Now, in terms of things that we can do here beyond that, so we can add experience replay. So our environment is dynamic. The compute node speeds change independently and may stay constant for a while and change back, so forth. Learning is, in a sense, sort of a weighted average of past experience. Over time, the impact of the old experiences will tend to dissipate. So if we switch to a different regime, then we might have some experiences in the past that are relevant. And if the agent has forgotten about those, then it's going to have to relearn them through trial and error, and that takes time. So what experience replay does is it stores a buffer of prior experiences, and then at the end of every episode, basically, it samples a batch of them, runs them through the learning functions, and updates. So, this isn't perfect, since obviously constantly relearning from the past diminishes how quickly we adapt to things that are changing in the present. So a balance really needs to be struck, partly determined by whether or not we feel that we have encountered all of the possible different regimes in the past. So how does this perform in comparison with before? Well, so here's our new graph, just using recall of 10 experiences per episode, which is obviously not a big number. But it's basically identical, so it didn't really have an impact. This is the new data, this is the old result. So those two are very, very similar, but that is kind of what we would expect in this particular case, because our environment, for the purposes of these results, is fairly stable. Unless we have things like changing speeds, we don't really expect to see a big benefit from experience recall on our problem set. And on top of that, the reality is that visualizing and measuring the performance on a per episode basis requires a good benchmark. And for the trivial case, we can use linear programming. When we look at the situations where different tasks require different amounts of work, or different compute nodes are on different speeds, then we can kind of get away with using integer programming, because we can't assign fractions of a piece of work to different nodes. But even that still doesn't include any information about the dependencies that are imposed from the graph. So that it becomes quite difficult to figure out how to express that, at least for me, in a sort of linear programming type context. So at some level, that's part of the reason to try and implement this in reinforcement learning in the first place. Another thing that people often do is to share the first layers of the two networks so that the actor benefits from the critic's learning rather than having to duplicate everything. However, we tried that. When we try that, we get this, which is obviously not so good. I feel like this is another clever idea that sort of fails to converge on any real problem. So it seems like it's okay for a little while, and then something clearly goes wrong around here, and then it just keeps relying on the cleanup node after that. It takes a long time to compute everything. Here we see all the work is indeed being done towards the end on this cleanup node, and the other ones are just sitting there idle. And now, I think this probably relates to a bias that comes from the state value being wrong in both the actor and the critic, and that causes the agent just to run off in the wrong direction and keep going. My instinct, and I may be wrong, but my instinct is that it's similar to something that Sebastian Thrun, who's the ex-Google self-driving car guy, wrote about in a paper back in 1993, where he talks about an overestimation phenomenon in connection with standard Q-learning. So Q-learning is obviously a different algorithm, but it uses approximators too. And I guess the idea is that if you have a bunch of states that have similar sort of values, and, well, the approximator inherently has noise. So if the values of these states are the true values are relatively similar, then the argmax function that they use in their policy for the agent will tend to take the agent to always go in the direction of the maximum noise. And as a result, it doesn't explore well, and it doesn't converge to good behavior. Now, we're not actually using an argmax here, because obviously our actor controls the policy. But it does appear that there is some similar behavior. And indeed, if we divorce the two values, we can't divorce them fully because the critic's loss function values feed into the actor loss functions. But if we do divorce them, then we do see the old graphs rather than new graphs. So clearly there is a benefit from splitting these two networks in our case. In conclusion, well, the ACTOR-CRITIC that we used finds a solution pretty well for distributing the set of tasks. It reflects a sort of a dynamic environment context where the compute node performance varies, and there are random subsets of tickets being updated at any time. It learns the dependencies between those tasks. It learns the amount of work effort that's required for each of those tasks. But in reality, finding the optimal result in each episode requires many forward valuations of two neural networks, which are non-trivial. And so the cost of dynamically finding the optimal schedule sort of renders it a little bit non-optimal. The architecture is also context dependent, so we tend to find that if you use too large a sort of neural network architecture with too small a problem domain, or too large problem domain with too small a neural network architecture, then it just doesn't converge. So there's definitely an art to finding some point where everything works together, which leaves me thinking that I have a little more work to do on this area. Anyway, so that's what I wanted to say. Do you have any questions?
Let's open the floor for questions. Does anyone have questions? Yes, please.
Just like a question on the graph you put recall. Is it the gamma that you put in that?
The recall is just the number of experiences from the past that we're going to rerun. So we randomly draw them and rerun them through the learning functions at the end of the episode.
Okay. So it's nothing to do with the because you talked about the decay and
No.
where do you have a decay and a discount?
No, it's a separate thing.
Okay. Yeah.
Yes, please.
Why did you say that you don't know precisely the reward? I mean, because you define time schedule as a reward.
Right, but the problem with that is just that at the start the agent has no idea what to do, so it just tries things at random, and it's not until it starts sort of seeing some benefit from some outcome that it is able to really improve. So just having the delta and the time as the reward is required, but intuitively it feels like there should be something more to that, just to encourage it to make better choices sooner rather than requiring hundreds of steps when only 3 are required.
I'll go ahead and answer the question. Did you consider, one thing that comes up with problems like this a lot is Byzantine failure. So if you have a specific machine that starts swapping or something and thinks it's alive, but it's very, very slow, would the system eventually just reschedule that task?
Yeah, we thought a little bit about it, but we haven't really done anything about that yet.
Yeah.
So I guess that's an obvious thing in the real world that would be required. So at the moment, the notion of speed is kind of assumed to be known. Right. So from at the moment you dispatch it, that's the speed at which you're going to receive it. And then it's the environment that takes care of making that happen. And it doesn't punish you for that. But yeah, in an ideal world, that would be more natural, if you like.
Right. Okay, great. Any additional questions? I think we've got time for probably one more question.
Good. All right. Thank you.